Now, in the lab we have conducted the experiment for determining the Cc, Cv and Cd. In that what we had done, we kept this head constant in a tank and we allow the water to come out through an orifice which is here. That may be, generally in our lab we have a circular orifice, but the orifice may have any kind of shape, right. When a jet emerges, then at somewhere which is approximately half of the diameter of the opening, this distance is half of the diameter of the opening, where d is the diameter of orifice, we have vena contracta at Cc. At Cc we have only one component of velocity, that is v, and it is only in x direction, right. And then jet emerges and it follow a trajectory. By measuring the trajectory we can relate the x and z to velocity, and we can find out this actual velocity by measuring x and z. And by measuring x and z we can find out the actual velocity, and theoretical velocity we can find out with the help of the formula, which is equal to root 2 gh, and in this way we can find out the Cv. And by collecting this water in a tank, we can find out the actual discharge, and theoretical discharge we can find out, and actual discharge divided by theoretical discharge is Cd. So, how to relate this x and z to v? Once a jet emerges out of this orifice at Cc, which is known as vena contracta, we have the velocity component only in x direction. Only in x direction we have velocity. So, because of this we can write that what happens to x and what happens to z. Now, we know that x is equal to ut, where u is the velocity of jet in x direction. So, x is equal to u into t, and we have studied that s is equal to ut plus half at square or gt square. Now, if we have velocity only in x direction and we do not have any velocity component in y direction, in that case what is distance travelled in y direction? Distance travelled in y direction will be z is equal to gt square divided by 2, because initially the velocity in y direction is 0, right. So, z is equal to gt square divided by 2. With the help of these two equations we can remove the t time component, and we can write u square is equal to gx square divided by 2z, and with the help of this formula we can find out the actual velocity of the jet at vena contracta, because we know g, we know x, we can measure in lab, we can find out z in the lab, and by knowing these values of x and z for a jet, we can find out at what velocity it is emerging and what is the velocity at the vena contracta. So, this is the actual velocity at vena contracta. And what is Cv? Coefficient of velocity. Coefficient of velocity is equal to actual velocity divided by theoretical velocity. And what is the theoretical velocity? We have studied that theoretical velocity v or u, whatever we want to call it, it is only in x direction. It is related to this h, which is kept constant in a tank, and this v is equal to root of 2g h. Here h is designated by capital H, so 2g capital H. This is the theoretical velocity without considering any loss. So, we can find out the Cv in this manner. So, substituting the value of u in this equation, we will get Cv, where Cv is equal to x divided by 4z h root. So, we know h, x, we know z, we know h, we can find out the Cv. Right. Once we know the Cv, and we can calculate the CD. We can find out the CC, because CC into CB is equal to CD, where CC is known as coefficient of contraction, CB is known as coefficient of velocity, CD is known as coefficient of discharge. How do we get CD? We have just discussed relationship, that CD is equal to, from this relationship, actual discharge divided by ideal discharge. For actual discharge, we can collect the water in a tank and we can measure it and we can write actual discharge, and ideal discharge, it is done with the help of A naught. What is A naught? It is the area of orifice, and root of 2gh, h is the height. In our case, it is designated by capital H, right. So, in this manner we can get these coefficient CC, CB, CD with the help of this simple experiment.